Okay, today we're gonna learn how to.
So suppose annual stock return follows this distribution. So expected return of the stock is mu per year, and then volatility variance of stock is sigma squared per year, something like that, which basically means that on the annual basis, let's say S is stock price, and which means we are basically assuming that this is per year, right? Per year. So this is mu is our expected stock return. Okay, expected stock return. So sigma square also is actually is expected stock variance for the next 1 year, which means that stock return. So S is today's stock price, so delta S is change of stock price. So this is stock return, right? This stock return, this means that this follows mu D, not D. Actually, we can change this one to the D. Okay. D is the change of stock price, so DT. Wow, it becomes thinner suddenly. DT. Interesting. Let me do it again. Oh. Yeah, so means that D is a change of the stock price. So today's stock price, so what change of stock price? Basically stock return. This is the definition of stock return. It means that this follows mu dt, right? When dt is 1, it means 1 year. When dt is 1 over 12, it is 1 month, and dt is 1 over 252, it is 1 day, something like that. And then dt, right? So if annual volatility is 20%, then 2-year volatility is 1 year variance is, let's say, 4%. Then 2-year variance is like 8%, which is approximately true if stock return is independent over time, right? Because this comes from right? This is because variance x plus y, right? Variance x plus y is variance x plus variance y if xy is independent, right? If xy is independent. If xy is independent, then variance x plus y is variance x plus variance y. So if stock return is independent over time, we can simply add variances, right? And this is also, natural, because of variance expectation of x plus y, right, is always expectation of x plus expectation of y, right? So if stock return is 10% per year for 2 years, it should be 20%. So this is the rate. We are expressing stock return in terms of rate, right? So dt is, when dt is 1, it is 1 year, right? And then from this one, we have an important thing, which is the st is basically s small t multiplied by e mu minus 2 sigma square, and the change of time, right? It is right. So this part is all continuous compounding, and then plus sigma root t minus small t, and then epsilon. Okay, where epsilon is standard normal distribution. right? And then the most interesting part is this part, right? This is for the convexity adjustment. And I explained why we have this term, because it is the difference between average return and so it is the return of average, and it is difference between return of average and average return, right? Which I explained. Do you remember why we have this term, right? You remember this, right? Right. This is the convexity adjustment that Taewoon asked a good question like 2 weeks ago. So anyway, so we have this one, right? Any question? This is very important. So assuming that we have this assumption, then we can express a stock return when stock return like a big T minus T time later is expressed this way, which is more simply if we express today's time as T, this is special case, but if today's time is 0, then of course we have mu minus sigma square 2 T plus sigma root T and the epsilon, right? Any question? Is everything clear? 질문 있어요? 김밀령 학생. 생각나요, 이거? So, again, let me explain again, because this convexity adjustment is important. So again, let's say there are 2 assets, year 1, year 2, and then returns. So asset 1, asset 2, suppose we have 2 assets. In asset 1, first period return is 10%, and second period return is minus 10%. Right? Asset is 0%. So return from the asset from first one, it was good for first 10%, and second year it was minus 10%. It is not so good. In year 2, it is always 0%. And then average return. Is what? Is average is, of course, it is always 0%. Okay? But it does not mean that we can actually earn 0% return if we invest money, right? So suppose our notional value is $100. S0 is 100. Then our money, value 1 and value 2, is that this one multiplied by 1 plus, okay, yeah, something like that. So I mean, return is 10%. So if we invest $100, first year return is 10%. Our money should be 110. It is the gross value of my asset. And then year 2, now we lose 10%. So this one multiplied by 1 plus this one. Right? So it is 99. So actually we are making money. So average of returns, average return is 0%, but actually we are losing money. So actually holding period return is then what? Holding period return is we invest $100, okay? We invest $100 and it becomes 99. Okay, then what should be the holding period return? Okay. This is the, so S0 1 plus holding period return 2 times. Okay, let's say more generally n times. Now it becomes st, right? Then if we are to calculate this in holding period return, then r equals st divided by s0 1 over n minus 1, right? So we can do that. So actually our holding period return divided by minus 1. Holding period return is actually, well, the other way around. What's going on? Yeah, this is F1, right? No. Yes. E4 divided by F1. Yes. So basically, we are losing money. So it is plus 10% minus 10% for your money. And of course, in second case, it is always 100. So this is the this is of course 0%, right? Well, actually, even the average of the return per year is 0% here, it does not mean that actually we are earning 0%. As we have more and more volatility, we are actually losing money. So this is the, let's make it percent. So this is minus, this is minus 0.5%. But if we increase variance, let's say 20% and 20%, then our return becomes even lower. Okay, we invest $100 and it becomes 96. So if we increase the variance more and more, actually our return decreases. It goes because of convexity adjustment. So we know that volatility is very bad, right? So the more volatility, the money actually we make decreases. And we have to take into account that when we simulate stock price. Therefore, even though, okay, even if stock price follow this process, so average of return per year is mu, and then variance is sigma square. Even though it is the case, if we have high variance, actual money we make should be lower. This is taken into account this part. Okay. Right. So this is actually the value of asset. So big ST is actually this one. Okay, or this one. And the actual holding period return, which is actually this part, becomes same to average return only when volatility is 0, like this one. Okay, when this is 0. Okay, so if we have a lot of samples, then in this case it is not clear whether this difference is exactly half of the variance. But if we have a large sample, the exact amount that we have to subtract because of the convexity effect is sigma square, half of sigma square. Okay. So we can do the simulation. So simulation, first we want to simulate this part. First, let's say, okay, let's say mu is, let's say, 10%, Actually, let's download the stock. 보경, do you have any stock in your mind? issued US stock. Name any stock. Apple. Okay. Let's download the Apple stock price. So historical stock price is download to spreadsheet. So we downloaded Apple, and then we don't need this part, and then we don't need this part. So average is no. So let's calculate return. Return is, let's make it continuous return. Okay, continuous return, continuously compounded return. It looks like this. And then average is what? Average. And then variance. Okay. And then annual return. We have to multiply this one. And then 252, and annual variance, and this actually for Apple it is very small, surprising. Okay, surprising. So annual volatility, root of this one, yes, it is small. Only 20%. Anyway, Apple is spectacular. You know, it is Apple, so it's a really spectacular performance. 40% per year with only 20% volatility. This is really spectacular because it's Apple anyway, right? So anyway, so when we just do the simulation, so basically mu is for Apple it is 40%, and sigma square is, or sigma is 21%. So we can do the simulation. So first, we can, let's say, time to maturity. And then let's say this is the 2.5 year. So suppose we want to simulate Apple's stock price 2.5 years later. And then let's call this is mu. Let's say this is mu, and then let's say this is volatility with sigma, and then this is what? This is the big T. Okay, first, so we simulate Z, epsilon. Okay. We simulate epsilon, which is the random number from standard normal distribution. We know how to do it. Norms inverse and rand. Okay. And then let's simulate how many. Okay. We simulate this one, and then let's then holding period return. Holding period return is what? This is mu minus what? Sigma square divided by 2 multiplied by t, right? Plus sigma and then square root of the t, and then this epsilon, right? So this is holding period return. So this is this part. This part, and then holding period return, and then therefore simulated stock price. Simulated stock price is then this is today's stock price. Let's say this is S0. Simulated stock price is, and of course S0 multiplied by EXP of this one. So we basically simulate the stock price. Okay? And then, of course, yeah. I mean, apparently, given that Apple's annual return is 40%, they are not surprised. They are all lot. Right? Yeah. They are all very high. So we simulated what? We simulated like 20 stock prices, and they are all greater than today's stock price. No wonder that annual stock return was 40% for us. So we are not likely to lose money if past stock return continue to future. Okay. Do you have any question? Okay. So if this is yes, Theo. Yeah, it is too high given that it is no wonder. It is Apple. Apple's stock return is very good. Yeah. If you cannot believe this, yes, it is even right. Look at this. It looks like 40%, right? So, if you bought stock of the Apple like 1 year ago, actually, this is, if you take a look at like 10 years, I mean, just the last 1 year is not. So last 1 year, Apple's stock price looks like this, 40%. Let's take a look at 10 years, right? It's even more spectacular. All time, even more spectacular, right? It is Apple, world's largest company. So I generate stock prices, okay? And then let's assume risk-free rate. And then risk-free rate. And the current US risk-free rate is, let's say 1%. And then let's call this one RF. Okay, so we simulate the stock price. And now we want to do the derivative pricing, and then, as you know, the key formula, okay, not formula, the key approach, our core approach of derivative pricing is risk-neutral valuation, right? The thing is that to recall your memory, okay, our approach is, this is very important, the most important thing we learned this semester. Okay. Our key approach, this is very important. Okay. For any, actually, not only derivative, for any asset prices, let's say V0 is today's asset price, which is, okay, we have to discount with risk-free rate of what? Expected value of an asset at time big T, right? But we need to put this one, totem, like top in the movie Inception, okay? To denote that this is expectation on the risk-neutral world, okay? So this was the most important formula of the financial engineering, derivative, and actually asset pricing, entirely asset pricing, okay? In order to calculate the price of an asset, what we do is we assume we are in the risk-neutral world, and then compute expected value of an asset at time big T at the risk-neutral world, and then discount it because we are at risk-neutral world. Okay, no one care risk. Therefore, we discount it with risk-free rate, and then which is basically asset price at risk-neutral world. And then the important theorem is that risk-neutral price, that asset price at risk-neutral world, should be exactly same to the real asset price in the real world. So that was the most important part. Okay. And so we are applying this formula. Okay. So if we are in the risk neutral world, okay, in the real world, past stock return of the Apple was 40% per year. But if we were in the risk neutral world, what would be the here? Okay, time to maturity 2.5 year. If we were in the risk neutral world, what would be the expected return of the Apple for the next 2.5 years? It should be risk-free rate, right? Because we are in the risk neutral world. And then if we believe Apple's expected return in that risk neutral world, if people think Apple's expected return is greater than risk-free rate, then everyone will gonna invest in Apple because they don't care risk, they only care expected return, right? So in equilibrium, anyway, Apple's stock price go up, which means Apple's expected return should down, or should go down up to until the expected return becomes exactly risk-free rate, right? So in this scenario, in the risk-neutral world, actually, we have to modify this one slightly. And then risk neutral, we have to modify this one slightly, and then we can only modify this part. Okay? We can only modify. So expected return should be R risk-free rate, right? R. And then because it is risk-free rate, we have to set this on hat because we are now going to generate random number in order to denote that we are generating random number at risk neutral world. Okay, so we are going to use this one. So next we are going to simulate stock price at risk neutral world. This is the okay, simulated stock price at risk neutral world. What we have to do is we have to slightly modify this one. So what we have to is stock price multiplied by, now we have to change, let's one by one. World is then what it should be now, expected return should be RF minus sigma divided by 2 multiplied by T plus, okay, sigma root T and then epsilon. Okay, now holding period return is significantly lower. And then simulated stock price is therefore S0 multiplied by expectation of this one. Okay. Why we have this annoying. Okay, so we simulated stock price at risk neutral world. Everything is the same. I'm just changing this mu into the R. That's all. Right? So we simulated stock price. Then, if we are interested in derivative pricing, then we are fine. Okay, let's calculate derivative price. Okay, suppose let's think of the put option. Let's say exercise price is 110. If exercise price is 110, and then if it is put option, today's stock price is this one, so definitely it is the what? It is out of the money option. No, actually it is in the money option, right? It is put option, so it is in the money option. So let's say it is a strike. Let's say it is a K, strike price K. Then simulated derivative price at risk neutral world, of course. World is max K minus this one, and then 0. Okay. So, right, in this case, simulated stock price is 167, and then exercise price 110. We are not gonna exercise at this time, right? Because we don't want to sell $167 asset at 110. We don't want to do that. So we don't want to exercise, so payoff from the derivative is 0. But in this case, it is out of money, but it is in the money, right? So this is this one. So this is in the money because it is asset price is stock price is 2091, and then we will gonna exercise it. We will send $91 Apple stock at 110. So we simulated derivative price at risk neutral world. So then, what is the expected derivative price? So EQ, expected value. Value is the average. Because of law of large numbers, average converges the expectation if we have very large sample, right? So expected value is this part, we computed this part, and all we have to do is discount it. So put option price is the, we have to discount it back. EFP minus RF, risk-free rate. And then multiplied by T, and then expected value. Then we have a put option price, right? So very simple, right? Then of course, whenever we refresh it, put option price changes because we did simulation too little. Okay, we have to do more simulation, right? And then we know that as we increase number of simulation, this expected value will converge. The true, actually this is average, but because of the law of large number, the average of large sample will converge to expected value. Then we are going to correct put option price. So actually, if we do the simulated infinite amount of time, this put option price will converge exactly to the price of the Black-Scholes formula. So this is the simple put option, but actually, right? Besides this one, we can compute more complicated derivative stock, right? If we are interested in sign of the stock price, then we simply change it into sign of the M2, something like that. Okay. So whatever company, suppose we are interested in, like very weird one, K multiplied by sine and then cosine of this one, right? This is a very strange asset. Then this is all okay. This is of course always positive. Then this is very strange asset, right? Very at the maturity, what they will give you is the max of 0, and then strike price minus strike price multiplied by sine and cosine of Apple stock price. It is fine. You can simply simulate derivative price like this, and it is actually always exercised. And in this case, the put option price is 100. Very simple. Right. Very simple. Okay. So anyway, yeah. Any question? So then, how to do the
Why do all the models always assume the
stock price move what?
Random. Because if we look at the simulation, like it always has those huge swings. I mean, it's of course probably because it's in the risk neutral world, but still, like it doesn't seem realistic if you also compare it to the real stock price that Apple had, for example.
Yes, so
90 and then up and 68 and then 200, like.
that's a good point. So if we compare this one and this one, yes, you're talking about this one, right? This is the simulated stock price in the real world, and that is the second one, the simulated and risk neutral. They are very different. Because in simulated stock price, I'm using expected return 40%, which is the past 1 year return. But when we actually simulate stock price, it is a future return. So we have to actually plug in expected return. But who knows what would be the expected return of the Apple? No one knows. But what we know is that although we don't know what would be the expected return of the Apple, maybe Apple lose money, right? Who knows? Because of Xiaomi, right? Something like that. Maybe Apple can lose a lot of money, right? Who knows? But what we actually know is that what we know for sure is that at least in risk neutral world, whatever happens, Apple's expected return should be exactly risk-free, right? Because people don't care risk, and in the risk neutral world, right? Yes, they should be risk-free, right? So they should be. It is natural that they are different. So anyway, we have to do the simulation, or rather we did only 20 times of simulation, which is too small. And then we want to do more simulation, right? And then if we are interested in more simulation, then what we can do, we can use Excel Visual Basic, right? So let's write down Excel Visual Basic. And then I have to say macro, okay? And then let's file name AAPL, okay? And put another one. And then I have to set up everything again. I have to set up okay. And then let's write the code. Okay. Okay. I think it is by now. I think you should enjoy coding. I think, but let's do it again. If you don't have laptop, you can move to Windows. Okay. And then let's insert a module, and then do the VBA simulation and a subroutine. Okay. So let's write the code. Okay, so stock price S0, Apple's stock price is what? Apple's stock price is, okay, in name of this one is tab 1, okay, tab 1. Apple's stock price is 109.7, and then sigma is what? It is this one. Okay. So Apple stock price today, annual volatility. Okay. And then what? Time to maturity, T. Let's say 2.5 years. Time to maturity. And then RF, risk-free rate is what? 1%. Okay. And then let's do the simulation. Number of simulation. Number of simulation is like say 100 times. Okay. And then for I, the 1, 2, simulation N. Next I, and then we will do 100 simulations. So fit tab 1. Okay, I'm gonna simulate it here, tab 1, and then cells, let's say I plus 1 and 1 is S0 multiplied by EXP RF minus sigma square divided by 2 multiplied by T. I'm just writing down this formula. Okay, just write down this formula. Plus sigma multiplied by T, the half multiplied by Z. Okay. Okay, Z. Well, this is 2 row. Okay. And then I have to define this epsilon, okay? Epsilon, okay? Random number. And then epsilon is I have to call worksheet function, and then I have to call norms inverse function and RND. Okay. In Excel Visual Basic, RND is random number from uniform distribution, and then actually this is still wrong, and then let's say holding period return is, let's say, I'll copy and paste this part. Holding period return is this way, and the expectation of H. So this is holding period return, and then it is the stock price at risk neutral world. Okay, actually, so we are done. We are done. And then I want to make a button. Right, I generate 100 stock price. Right? 100 stock price. Actually, but thing is that I don't actually have to what? Simulate. I don't actually have to see the real number in Excel sheet basically. So I don't need this one actually. So I'll simply store. Okay. I want to simply store the value as a ST. ST, right? ST, the final stock price. And then let's say K is the strike price, is 110. This is the number of simulation. K is the stock price. Then I can price put option price. Put option is the what? I have to get the put option pair with max. I have to call worksheet function again in order to do max, and the max of the ST, K minus ST, and 0. Right? K minus, this is put option price. Okay, but then now for one simulation, I calculate the put option price. So next, what I have to do is let's define option value, which starts from 0, and then I collect option value. Let's make it more simple. So let's define this one is the put option value at I. Okay. Simulated put option value. Simulated put option value. And then my put option value, put option equals, in order to correct add all simulated put option value, I add put option plus simulated put option. Then think about what it's gonna do. What it does, initial put option value was 0, and then for next put option value, I add simulated put option value to the previous put option value and add it. Add one more time, then it is the previous put option value and add this one again. And I keep doing this one. I mean, keep adding simulated stock prices. 100, how many times? In this case, 100 times. Do you know what I'm doing? 무슨 말인지 알겠어요? Right? It starts from 0 at one iteration. It adds simulated stock price. No. New put option value is simulated. And 2 times, now my put option value is previous simulated stock price, and I'm adding another simulated put option value. So I have a sum of the 2 simulated put options. And then if I do it again, I'm adding 100 put option, simulated put option prices, right?
You have to define it a little differently, right? Because it's 2 times put up equals put up.
Yeah, it should be, this one and this one should be different, right? So this was the simulated put option is a simulated value at the time, at the one particular simulation. And then this put option is the sum of every put option value. And my final put option value is my final put option value is what? I have to do is put option value, previous put option value divided by number of the simulation. Right? Number of simulation. And I have to do the discounting. Right? Done. This is my put option value. Right? And then what I'm going to do is I want to print out this one. And then, so let's say sales 1 is option value, and sales 1, 2 is I'm print out put option value. And if I run it, done. And of course it changes because it is I have only 100 simulation. And if I increase number of simulation, right, like this is 10,000 times, no, 100,000 times, 10 to the power of 5, then its value should be, it takes more time, but much more stable, right? Right, now it changes around 13, okay? So it becomes a much more stable value. So this is done. Very simple, right? Let me delete this one. I don't need this one. What a simple way of calculating option value. Any question, Nicholas? It's simple, right? This is the, I mean, this coding is essentially not that important. The important one is actually this one, right? We are using this formula. Right? You are simulating option value, maturity, at the risk-neutral world, get the average and discount it. Done. Right? Felix, any question?
No,
It's okay, right? It's very fun, isn't it?
yeah.
And you know, it is extremely useful technique. Okay?